Have you ever looked up at the night sky and felt a sense of awe, only to realize that what you're seeing is just the tiniest fraction of what's actually out there? Beyond the familiar stars and swirling galaxies lies a hidden cosmos, one that isn't illuminated by starlight, but shrouded in shadow and mystery. These are the dark galaxies, cosmic phantoms that challenge everything we thought we knew about the universe. They're made up almost entirely of dark matter, an invisible substance that doesn't emit, absorb, or reflect light, making them nearly impossible to detect with traditional telescopes. Yet their gravitational influence is undeniable, warping space and twisting the paths of light itself. Scientists fear these ghostly structures not because they pose any direct threat to us, but because their existence forces us to confront how little we truly understand about the cosmos. Imagine an entire galaxy, vast and ancient, drifting through space with almost no stars to mark its presence, a silent, invisible leviathan moving through the cosmic dark. For decades, astronomers speculated about such objects, but it wasn't until recent advances in technology and observation that we began to uncover them. These dark galaxies defy our expectations, challenging the very models we've built to explain how galaxies form and evolve. Some appear to be failed galaxies, places where star formation never truly took off, while others might be remnants of cosmic collisions or the hidden scaffolding upon which visible structures are built. Whatever they are, each discovery raises more questions than answers, pulling us deeper into a mystery that touches on the fundamental nature of reality itself. In this video, we'll journey into the heart of that mystery as we explore 25 of the most enigmatic dark galaxies ever discovered. From the haunting depths of Dragonfly 44 to the perplexing void of Antlia 2, each of these cosmic anomalies holds secrets that both fascinate and unsettle the scientific community. We'll uncover why researchers speak about them with a mixture of excitement and trepidation, and what their existence could mean for the future of astrophysics. This isn't just a tour of strange celestial objects, it's an invitation to rethink what we know about the universe and our place within it. So join us as we venture into the shadows where the rules of physics seem to bend and the cosmos reveals its most carefully guarded secrets. Our journey into the shadows begins with one of the most perplexing discoveries of the modern astronomical era, a ghost in the Coma cluster known as Dragonfly 44. This galaxy, spotted by a specialized telescope array literally called the Dragonfly telephoto array, appeared at first glance to be a faint, diffuse smudge of light, a cosmic wisp that seemed barely worth a second look. But as researchers studied it further, they realized they were looking at something that defied all logic. Here was an object the size of our own Milky Way, a colossal structure with the mass of 1 trillion suns, yet it emitted less than 1% of the light a galaxy of that scale should. The numbers were so baffling that scientists had to conclude that this galaxy is made up of 99.99% dark matter. It is a place where the visible universe, the stars and gas we can see, is nothing more than a fleeting afterthought, a few scattered fireflies in an otherwise impenetrable dark. The sheer dominance of dark matter in Dragonfly 44 creates a gravitational pull that is immensely powerful, enough to keep its sparse stars from flying apart into the void. Yet, for some reason we still cannot explain, that immense gravitational potential never sparked the furious star formation we see in other galaxies. It's as if the entire galaxy is a cosmic engine that was built and primed to create stars, but someone or something simply forgot to turn the key. This presents a direct challenge to our understanding of how dark matter behaves. Our leading models suggest that dark matter should act as a scaffolding, pulling normal matter together to eventually light up with the birth of new stars. Dragonfly 44 suggests that this process can fail on a spectacular scale, leaving behind a silent, dark leviathan. This single, bizarre object forces us to ask a deeply unsettling question. Is Dragonfly 44 a unique cosmic oddity, or is it a prototype? Could the universe be teeming with such dark giants, an entire hidden population of galaxies that have simply remained invisible to us? Its discovery in the dense Coma cluster is also a vital clue, suggesting that its environment may have played a role in stripping away its gas or otherwise halting its development, leaving behind this ghostly relic. Every new observation peels back another layer of its mystery, compelling scientists to re-examine the fundamental rules of cosmology and wonder what other secrets are waiting in the dark. While the sheer scale of Dragonfly 44 boggles the mind, our next dark galaxy proves that you don't need to be a colossal giant to pose a colossal mystery. Lurking right in our own cosmic backyard, a mere 420,000 light-years from Earth, is the ghost of Antlia II. This faint dwarf galaxy is a satellite of our own Milky Way, but it is so incredibly diffuse with such an extremely low surface brightness that it managed to hide in plain sight for decades, completely invisible to every sky survey until the European Space Agency's Gaia spacecraft turned its ultra-precise eyes toward that patch of sky. Gaia wasn't even looking for new galaxies. Its primary mission is to map the precise positions and motions of billions of individual stars within our galaxy. But in its data, astronomers found something completely unexpected: a subtle, coherent wobble in the motion of a specific group of stars, a telltale sign that they were all gravitationally bound together as part of a single, vast structure that was otherwise completely unseen. What makes Antlia II so deeply puzzling isn't just that we failed to see it for so long, but its bizarre physical properties once we finally did. This is a galaxy that is far too big for its brightness. In terms of physical size, it's as large as the Large Magellanic Cloud, another one of our Milky Way's satellite galaxies. But whereas the Large Magellanic Cloud blazes with billions of bright, new stars, Antlia II is utterly anemic, emitting almost no light at all. If you were to somehow float next to it, you would likely see nothing but a barely perceptible ethereal haze against the blackness of space, a phantom smudge of a few old, dying stars. And this is where the dark matter fear truly takes hold. For this wispy collection of stars to hold itself together against the immense tidal forces of the Milky Way, it must be embedded within an absolutely massive and massively dense halo of dark matter. The calculations are what truly unsettle scientists: to have the gravitational strength to keep its stars from being instantly shredded and scattered into the void. Antlia II must be one of the most dark matter-dominated objects we've ever found. Its dark matter halo is far denser and more massive than any standard model of galaxy formation can easily explain for an object of its size and star count. It behaves less like a typical dwarf galaxy and more like a ghostly, concentrated knot of pure dark matter that just happens to have a few stars caught in its gravitational web. This presents a direct challenge to our understanding of how such satellite galaxies form and evolve around larger hosts like the Milky Way. Its mere existence suggests that our models of dark matter's behavior on small scales might be incomplete or, in the worst-case scenario, fundamentally flawed. This leads to the most profound fear raised by Antlia II's discovery. If something this large, this massive, and this close to us could remain hidden for so long, what else is lurking in the shadows of our own galactic halo? How many other dark, massive ghosts are orbiting the Milky Way, unseen and undetected, their silent gravitational tugs subtly influencing the motion of our own sun and the delicate dance of the stars we can see? Antlia II is a sobering reminder that we are still mapping the darkest corners of our own home, and that our galaxy's history and future may be dictated by forces we are only just beginning to sense. Moving even deeper into the realm of the nearly invisible, we encounter a galaxy so faint it was named for the very act of transition, a cosmic waypoint in the dark. This is Segue 1, and it holds the distinction of being one of the darkest galaxies ever confirmed. To call it a galaxy in the traditional sense feels almost like a misnomer. Imagine a structure that spans hundreds of light years, yet contains only a few hundred ancient, dim stars. If you could stand within it, the night sky would be nearly empty, a profound and terrifying blackness punctuated by just a handful of faint, distant pinpricks of light. This is not a place of creation, but a relic of a forgotten era, a skeleton of a galaxy whose visible matter is almost an afterthought. The true nature of Segue 1 is revealed not by what we can see, but by the immense gravitational force holding its meager stars together. The motions of those few hundred stars are frantic, whipping around at velocities that should instantly tear the entire structure apart. The only possible explanation is that Segue 1 is overwhelmingly composed of dark matter, with a mass-to-light ratio that is among the highest ever measured. For every single photon of light its stars emit, there is an incomprehensible amount of invisible mass holding the entire system in a vice-like grip. It is a dark matter anchor, a concentrated knot of the universe's most mysterious substance that simply has a few stars tragically caught in its web. This is where Segue 1 moves from a curiosity to a central player in one of cosmology's most enduring puzzles, the missing satellite problem. Our leading model of the universe, the lambda-cold dark matter model, predicts that large galaxies like the Milky Way should be surrounded by a vast swarm of thousands of smaller dwarf satellite galaxies. Yet for decades we could only find a few dozen. This glaring discrepancy suggested something was terribly wrong with our simulations or our understanding of dark matter. Segue 1 is a vital piece of that puzzle. It represents the predicted population of ultra-faint, dark matter-dominated satellites. They weren't missing, they were just so incredibly dark that we lacked the technology to see them. The fear it instills in scientists is not about the object itself, but about what it represents. Segue 1 is not an anomaly, it is likely a prototype. Its discovery proved that galaxies can exist with almost no stellar component, behaving essentially as pure dark matter halos. If Segue 1 is a template, then the dark halos predicted by our simulations aren't empty. They are everywhere, each potentially harboring a few dozen stars or perhaps none at all, completely invisible to our telescopes. This means the cosmos could be filled with a hidden architecture of dark galaxies, a ghostly framework that outnumbers the luminous galaxies we see. Our Milky Way's halo might not be missing satellites after all. It might be teeming with them, a vast collection of dark ghosts like Segue 1, silently shaping the gravity of our galaxy from the shadows. But if Segue 1 represents the dark, silent ghosts of the cosmos, our next galaxy suggests something far more energetic and potentially terrifying lurking in the void. Tucked away in the faint constellation of Triangulum, a mere 30,000 light-years from Earth, lies Triangulum II, an ultra-faint dwarf galaxy that presents a paradox of monumental proportions. On the surface, it appears similar to Segue 1, a tiny, wispy collection of ancient stars, so dim that it was only discovered in 2015 by the Panoramic Survey Telescope and Rapid Response System. Its handful of stars are barely held together, a flickering signal in the vast dark that should, by all rights, be instantly torn apart by the Milky Way's gravity. Yet it persists, and the reason why has sent a ripple of excitement and apprehension through the astrophysics community. The key to Triangulum II's mystery lies not in its visible light, but in the invisible, high-energy radiation it seems to emit. When astronomers pointed NASA's a Fermi gamma-ray space telescope in its direction, they detected a faint but significant spike of gamma-ray photons emanating from its core. Gamma rays are the most energetic form of light in the universe, typically produced by the most violent events imaginable: supernova explosions, neutron star collisions, or matter falling into supermassive black holes. But Triangulum II has none of those things. It possesses no recent supernova remnants, no energetic pulsars, and certainly no central black hole. It is a stellar graveyard, a quiet and ancient place that should be virtually inert. So what, then, is producing this intense radiation? The most thrilling and concerning hypothesis is that we are witnessing the signature of dark matter annihilation. This idea stems from a leading theory about the nature of dark matter itself, that it could be made of weakly interacting massive particles, or WIMP. According to this model, when two WIMP collide, they could annihilate each other in a flash of energy, producing secondary particles that then decay into the gamma rays we detect. If this is true, then Triangulum II isn't just a passive halo of dark matter. It is a cosmic reactor, a place where the very fabric of the unseen universe is revealing itself through self-destruction. The galaxy's extreme density of dark matter would make it the perfect environment for such rare particle collisions to occur frequently enough for us to notice. This possibility is what fuels both scientific excitement and profound fear. Confirming dark matter annihilation in Triangulum II would be one of the most significant discoveries in the history of physics, finally allowing us to identify the particles that make up 85% of the matter in the universe. It would open a direct window into a realm of physics beyond the standard model, the current rulebook for particle physics that is notoriously incomplete. However, the implications of such energetic processes are also deeply unsettling. The gamma-ray signal, if indeed from annihilation, implies that dark matter particles are interacting with each other in ways we never anticipated, possessing properties and energies that are entirely foreign to our current understanding. It suggests that dark matter might be more complex and potentially more active than the inert, invisible scaffolding we've always assumed it to be. The fear is not that Triangulum II poses any danger. It is far too distant for that. The concern is for the integrity of our fundamental models of the universe. If dark matter can annihilate, it means our entire conception of this mysterious substance has been too simple. It could mean that dark matter has a rich, hidden physics of its own, with forces and interactions operating completely independently from the visible universe we inhabit. This wouldn't just add a new chapter to physics textbooks, it would tear up the old ones and force us to start anew. Triangulum II, a faint smudge of light in our backyard, therefore holds the power to either validate our quest to understand dark matter or reveal that it is far stranger and more intimidating than we ever dared to imagine. Yet for all the potential energy locked within Triangulum II's dark core, our next discovery presents a paradox of an entirely different nature, a ghost so vast and yet so faint that it seems to defy the very logic of gravitational physics. Hovering around 70,000 light-years away in the constellation of Crater is a cosmic phantom known as Crater II. Despite being the fourth largest dwarf galaxy known to orbit the Milky Way, this celestial giant is so incredibly diffuse with such a miserly output of light that it remained completely hidden from us until 2016. Its discovery was not the result of seeing a new smudge of light in the sky, but of sophisticated computer algorithms meticulously sifting through data from the VIRTI survey telescope in Chile, identifying a subtle, coherent overdensity of very old, very faint stars. The moment its true nature was understood, it sent a shockwave through the astronomy community. Here was a galaxy the size of the Large Magellanic Cloud, but with 10,000 times fewer stars, making it one of the largest and most low-surface brightness objects ever found in our local universe. The most immediately unsettling feature of Crater II is its physical appearance or lack thereof. Astronomers often describe it with words like fluffy, puffy, or diffuse, which belie the profound weirdness of this structure. Its stars are not concentrated in a tight core, but are instead scattered across a sprawling volume of space, forming a gigantic, ethereal haze that is almost impossible to distinguish from the black background of the cosmos. If you could view it from the side, it wouldn't look like a classic pinwheel-shaped galaxy or even a compact globular cluster. It would resemble a wisp of cosmic smoke, a tenuous and fading breath held in the gravitational grip of something unseen. This extreme diffuseness is its greatest mystery. A structure this large and this loose should be incredibly fragile, easily shredded and dissolved by the immense tidal forces of our much more massive Milky Way galaxy. The fact that it hasn't been torn apart implies that it is being held together by a powerful, invisible force, a massive and dense halo of dark matter. This is where Crater 2 moves from being a mere curiosity to a direct challenge for our most trusted theories. The standard model of dark matter, known as cold dark matter, posits that dark matter particles move relatively slowly and clump together readily, forming dense, gravitationally powerful halos that act as seeds for galaxy formation. These halos should have a certain predicted density profile, meaning they are much denser at their centers and become more diffused toward their edges. Crater 2's dark matter halo, however, appears to be far too fluffy and spread out to fit this model. Its core is not dense enough. It behaves less like a concentrated knot of dark matter and more like a vast, ethereal cloud of it. This mismatch suggests that our simulations of how dark matter behaves on the scale of small galaxies might be missing a crucial piece of physics. The fear that Crater 2 instills in researchers is not about the galaxy itself, but about what it reveals regarding the potential weaknesses in our foundational cosmological models. Its existence suggests that dark matter particles might interact with each other in ways we haven't accounted for, perhaps through some unknown force that prevents them from collapsing into the denser cores our models predict. Alternatively, it could indicate that the violent evolutionary history of the Milky Way satellite system, full of galactic collisions and near misses, has somehow puffed up Crater 2, stripping away its stars and stirring up its dark matter in a process we don't fully understand. Either scenario forces our uncomfortable realization that the dark matter halos which form the bedrock of our universe's large-scale structure might be far more complex and varied than our tidy simulations have led us to believe. Crater 2 stands as a silent, fluffy monument to our ignorance, a reminder that the most common substance in the universe still has the power to surprise and confound us. Leaving the faint ghosts of our own galactic neighborhood behind, we now cast our gaze across the intergalactic void to our closest major galactic rival, the Andromeda Galaxy. Orbiting this colossal spiral is a satellite that epitomizes the theme of hidden giants, Andromeda 19. This enormous structure is a satellite galaxy of Andromeda, and it is so sprawling and ethereal that it essentially redefines what we think of as a galaxy. Its stars are scattered across a vast volume of space, creating a dim, tenuous haze that is incredibly difficult to distinguish from the background sky. In fact, its surface brightness is so low that it is literally as faint as the natural airglow of Earth's own atmosphere, which is why it remained undetected for so long, hiding in plain sight despite its immense physical scale. The paradox of Andromeda 19 lies in its contradictory properties. It possesses a physical diameter that is truly enormous for a dwarf galaxy, stretching across tens of thousands of light years. If it were brighter, it would be a prominent feature in our night sky, yet for all that immense size, it contains a pitifully small number of stars. The entire galaxy emits less than 1% of the light that a typical object of its size should. This means the ratio of dark matter to luminous matter in Andromeda 19 is among the highest ever measured. It is not merely a galaxy with a dark matter halo. It is a dark matter halo that has managed to capture a scant sprinkling of stars, a ghostly net cast across the cosmos with almost nothing caught in its weave. This discovery forces a profound and unsettling realization about our place in the universe. Andromeda 19 is not some rare, distant anomaly. It is a satellite of the galaxy next door, part of our local group of galaxies. If such a massive, dark object can exist this close to us without being detected until recently, how many more are out there? Our entire map of the local universe, the cosmic neighborhood we thought we knew so well, might be fundamentally incomplete. We have been charting the cosmos based on the light we can see, but Andromeda 19 is a stark warning that our maps could be missing the largest and most massive structures simply because they don't glow. The fear that Andromeda 19 instills is not about the object itself, but about the integrity of our cosmic senses. For decades, astronomers have used the observed motions of galaxies within clusters to estimate their total mass, leading to the original discovery of dark matter itself. But if space is peppered with these enormous dark galaxies that we cannot see, then our mass estimates for the local universe could be significantly off. These hidden giants would exert a gravitational influence on everything around them, subtly tugging on galaxies we can see and distorting their paths through space. We might be misinterpreting the cosmic dance, attributing motions to the pull of visible mass when, in fact, invisible leviathans like Andromeda 19 are leading the dance from the shadows. This galaxy is a haunting reminder that the universe is not only stranger than we imagine, but that it may be actively concealing its truest, most massive form from our prying eyes. While Andromeda 19 reveals the sheer scale of dark galaxies, its cousin, Andromeda 21, presents a different kind of puzzle, one focused on the intricate and unexpected architecture of dark matter itself. Discovered around the same time, this satellite galaxy also orbits the mighty Andromeda, but its story is less about being hidden and more about being strangely inefficient. Andromeda 21 has all the ingredients for a thriving galaxy: a massive dark matter halo to provide gravitational scaffolding and a reservoir of gas from which to birth new stars. Yet, for reasons we are still struggling to understand, it has consistently failed to light up the cosmos in any significant way. Its star formation has been anemic at best, a slow and sputtering process that has left it incredibly faint, its few stellar inhabitants old and lonely. The central mystery of Andromeda 21 isn't just its lack of stars, but the bizarre and seemingly contradictory structure of the dark matter halo that surrounds it. According to our most sophisticated computer simulations of galaxy formation, a halo of this mass should have a very specific density profile. It should be incredibly dense and tightly packed at its core, creating a powerful gravitational well that efficiently pulls in gas, compresses it, and triggers the firestorm of star birth we see in most galaxies. However, observations of the motions of Andromeda 21 stars tell a different story. They suggest that its dark matter halo is far less concentrated than the models demand. The core is mysteriously fluffy, lacking the intense gravitational focus that should be there. It's as if the galaxy's central engine is misfiring, possessing immense power but unable to channel it effectively to get the job done. This discrepancy between prediction and observation is more than a minor academic detail. It strikes at the very heart of our understanding of how the universe builds galaxies. The cold dark matter model has been spectacularly successful at predicting the large-scale structure of the cosmos, the vast cosmic web of filaments and clusters that define the universe. But on the scale of small dwarf galaxies like Andromeda 21, it consistently seems to fail. The models predict overly dense and centrally concentrated dark matter cores, creating what astronomers call the core cusp problem. They simulate a cusp, a sharp peak in density at the center, but we repeatedly observe a core, a much shallower and more distributed distribution of dark matter. Andromeda 21 is a prime example of this problem, a clear data point showing our simulations are missing a key piece of physics. This forces scientists to confront several deeply unsettling possibilities. Perhaps dark matter isn't completely cold and non-interacting as we've long assumed. Maybe dark matter particles can interact with each other through some unknown force, generating pressure that prevents them from collapsing into the dense cusps our models predict. This would be a revolutionary concept, suggesting dark matter has a rich and complex physics all its own. Alternatively, the answer might lie in the often violent evolutionary history of these small galaxies. The intense gravitational tides from a host galaxy like Andromeda, or powerful bursts of early star formation that blow out gas and energy, could have physically stirred up the dark matter, scattering it and eroding the central cusp into a shallower core over billions of years. Andromeda 21, therefore, is not just another dark galaxy. It is a critical test case, a natural laboratory forcing us to question the fundamental properties of the universe's most abundant material. Its existence suggests that the rules of galaxy formation are far more complex and nuanced than our simulations can currently capture. Each faint star within it is a silent witness to a billion-year history we are only beginning to decipher, a history that may require us to rewrite the physics of the dark universe to finally understand. As we venture deeper into the enigmatic satellites of our neighboring galaxy, we encounter Andromeda 25, a celestial object that pushes the concept of a dark galaxy to its absolute extreme. Discovered within the vast survey data of the Sloan Digital Sky Survey, this dwarf spheroidal galaxy orbiting Andromeda initially registered as little more than a subtle statistical fluctuation, a faint and diffuse clustering of a few thousand ancient stars. Its unassuming appearance, however, belied a terrifying secret hidden within its gravitational grip. When astronomers measured the velocities of its stars, they found them whipping around at speeds that were simply impossible for the meager amount of starlight they could see. The calculations that followed revealed a mass-to-light ratio so staggeringly high that it placed Andromeda 25 among the darkest galaxies ever identified, a place where dark matter outweighs visible matter by a factor of thousands to one. The technique used to unmask this cosmic phantom is a testament to astronomical ingenuity, relying entirely on the subtle interplay of gravity and motion. By using powerful spectrographs on telescopes like the Gemini North Observatory, scientists can measure the slight Doppler shifts in the light from individual stars within the galaxy. A star moving away from us has its light stretched to redder wavelengths, while a star moving toward us is shifted toward blue. By meticulously tracking these shifts for dozens of stars across Andromeda 25, astronomers can map out their orbital velocities. The results were shocking. The stars were moving so rapidly that the gravitational force required to keep them from flying off into intergalactic space had to be immense. The only source for that force is a colossal, dense, and utterly invisible halo of dark matter, a gravitational anchor of unimaginable proportions holding this wispy collection of stars together against all odds. This profound darkness is what leads to a deeply concerning hypothesis about Andromeda 25's origins. Many theorists now suspect it is not merely a faint galaxy, but a fossil, the remnant of a failed galactic formation from the dawn of time. In the early universe, vast clouds of dark matter and pristine gas should have collapsed to form the first generations of galaxies, but for some, the process may have been catastrophically inefficient. Perhaps Andromeda 25 formed in a region where the gas was too hot or too turbulent to cool down and condense into stars effectively. Or maybe it experienced a traumatic encounter early in its life, having its star-forming gas violently stripped away by a close pass with another galaxy, leaving behind only its dark matter skeleton and a handful of stars that had already formed. It is a cosmic tragedy on a billion-year scale, a structure that had all the potential to become a brilliant island of stars but instead became a ghost, frozen in time as a monument to what might have been. The fear that Andromeda 25 inspires is not about its own existence, but about what it implies for the history of the universe. If this object is indeed a fossilized relic of a failed formation process, then the cosmos could be littered with such dark remnants. These silent, invisible structures would represent a vast and missing chapter in the story of galactic evolution, a population of cosmic dead ends that our telescopes designed to see light are almost entirely blind to. Their sheer numbers would mean that our current census of the universe's mass and structure is woefully incomplete, and our understanding of how galaxies are born is missing a fundamental piece of the puzzle. Andromeda 25 stands as a stark, dark sentinel, forcing us to question not only what is out there, but how many entire histories of the universe have unfolded in perfect silence, completely hidden from our view. Journeying next into the heart of one of the universe's most crowded neighborhoods, we find VCC 1287, a galaxy that has mastered the art of survival in a cosmic war zone. This low-surface brightness galaxy resides in the Virgo cluster, a chaotic gathering of over 2,000 galaxies all bound together by gravity, constantly interacting, colliding, and tearing each other apart. In such a dense and violent environment, a small, faint galaxy like VCC 1287 should be the equivalent of a small boat in a hurricane, easily shattered and consumed by its larger, more powerful neighbors. The immense tidal forces generated by passing galaxies should have ripped it to shreds billions of years ago, scattering its stars into the intracluster void. Yet there it is, persisting against all odds, a tenacious and coherent structure that has weathered the storm for eons. Its survival is the central mystery that points directly to a hidden source of immense strength. Astronomers studying VCC 1287 have found that the motions of its stars indicate a gravitational hold far more powerful than the visible mass of the galaxy could possibly provide. The only explanation is that it is enveloped in a massive, dense halo of dark matter, a protective shield that acts as a gravitational anchor. This dark matter cocoon provides the structural integrity needed to resist the relentless tidal pulling from other galaxies in the cluster. It's as if this faint wisp of light is actually the tip of a colossal, invisible iceberg, with the vast majority of its mass lying hidden beneath the surface, unbudging and unbreakable. This remarkable resilience forces a deeply concerning question about the true population of galaxy clusters. If a galaxy as faint as VCC 1287 can survive in the most dangerous environment imaginable solely because of its dark matter content, how many other similar galaxies are out there, completely invisible to us? Our current surveys of clusters like Virgo are heavily biased toward finding galaxies that emit a lot of light. We catalog the brilliant spirals and giant ellipticals, but we could be entirely missing a hidden population of ultra-dark, tenacious dwarfs that are just as numerous, if not more so. These dark galaxies would be the true survivors, the invisible backbone of the cluster, contributing significantly to its total mass without ever revealing themselves through starlight. The fear surrounding VCC 1287 is not about the object itself, but about the integrity of our maps of the cosmos. Galaxy clusters are the largest gravitationally bound structures in the universe, and we use them as crucial laboratories for measuring cosmic parameters, including the total amount and distribution of dark matter. If these clusters are filled with a large number of undetected, dark matter-dominated galaxies like VCC 1287, then our current mass estimates for these clusters could be significantly underestimated. We might be misreading the gravitational dynamics of the entire cluster, attributing the pull we see to the visible galaxies and a smooth distribution of dark matter, when in fact a substantial portion of that mass is locked up in these invisible, resilient islands. VCC 1287 is a single, faint clue that the most crowded places in the universe might be far more populated and far stranger than our telescopes have ever been able to show us. But just as we begin to accept the idea that dark matter is an inescapable, fundamental ingredient of every galaxy, the universe presents us with a shocking outlier, a cosmic rebel that seems to defy the very rules it helped create. This is NGC 1052DF2, a galaxy that sparked one of the most intense and passionate debates in modern astronomy because it appeared, against all odds, to contain almost no dark matter at all. Its discovery was not just surprising, it was nearly heretical. For decades, the existence of dark matter had been inferred from the simple, consistent observation that galaxies rotate too fast for the gravity of their visible matter to hold them together. Dark matter was the necessary, invisible glue. Then along came DF2, a ghostly, ultra-diffuse galaxy in the constellation Cetus, which upon first inspection seemed to be missing this glue entirely. The motions of its star clusters were sedate, calm, and slow, perfectly matching the gravitational pull expected from its paltry collection of stars and gas. It was as if we had found a car speeding down the highway without an engine, a building standing tall without a foundation. This wasn't just a new galaxy, it was a direct challenge to a foundational pillar of cosmology. The initial analysis was so startling that it forced astronomers to question everything about the object, starting with its distance. The entire argument that DF2 lacked dark matter hinged on one critical measurement: how far away it is. Distance is the key that unlocks all other properties. If the galaxy is closer to us, then its stars are intrinsically dimmer, meaning there are actually more of them than we thought to account for the light we see. More stars means more visible mass, which could explain the observed star motions without needing dark matter. But if it is farther away, then its stars must be intrinsically brighter giants, meaning there are fewer of them. With less visible mass, the star motions would require a massive dark matter halo to make sense. The original team, using the Hubble Space Telescope's keen vision to measure the brightness of old red giant stars, placed DF2 at a distance of 65 million light-years. At that range, the numbers showed a stunning absence of dark matter. This conclusion sent a shockwave of fear and excitement through the scientific community. The fear was not that our models were wrong, but that they might be incomplete in a way nobody had predicted. If a galaxy can form without dark matter, it throws the entire theory of galaxy formation into disarray. Our leading models posit that dark matter halos form first, acting as gravitational wells that draw in normal gas, which then cools and condenses to form stars. Take dark matter out of the equation, and you remove the very foundation of that process. How did DF2 gather its stars? What force collected them and holds them together? Its existence suggested there might be an entirely different, unknown pathway for building galaxies, a second cosmic recipe we never knew existed. The controversy exploded when other teams reanalyzed the data and proposed a different distance. Using the same Hubble images but different analytical techniques, they argued the galaxy was much closer, around 42 million light-years away. At this shorter distance, the galaxy's stars would be fainter, implying there are more of them. This increased visible mass could then easily account for the observed motions of the star clusters, rendering the mysterious lack of dark matter null and void. The debate became a technical, complex tug-of-war over methods of measuring cosmic distances, a fundamental yet notoriously tricky aspect of astronomy. The fear now pivoted to a different concern, that our tools might not yet be precise enough to answer such a profound question, leaving us in a state of frustrating uncertainty. This ongoing mystery is what makes DF2 so uniquely frightening to scientists. It represents a lose-lose scenario for our current understanding. If the original distance is correct and the galaxy truly lacks dark matter, then we must explain how it came to be, forcing a dramatic rewrite of astrophysics. If the revised, closer distance is correct, then the galaxy is perfectly normal, but the controversy reveals a terrifying fragility in our measurement techniques. It shows that even with our most powerful telescopes, we can still be fundamentally unsure about the basic properties of a relatively nearby galaxy, casting doubt on the certainty of other cosmic discoveries. NGC 1052 DF2, therefore, stands as a monument to scientific humility. It is a ghost that haunts us not with what it is, but with the uncomfortable questions it forces us to ask about the limits of our own knowledge and the confidence with which we claim to understand the universe. If the controversy around DF2 felt like a tremor in the world of cosmology, then its celestial neighbor, NGC 1052 DF4, was the earthquake that followed. Discovered in the same patch of sky and part of the same galactic group, DF4 appeared to be a carbon copy of its enigmatic sibling, another ultra-diffuse ghost of a galaxy that, upon initial measurements, seemed to be almost entirely devoid of dark matter. The discovery of a second such object was profoundly more unsettling than the first. One anomaly could be written off as a bizarre fluke, a cosmic one-off that defied categorization. But two suggests a pattern. 2 implies that whatever process created DF2 wasn't a unique accident, but a repeatable phenomenon, a new class of celestial object that our models never predicted. The initial observations of DF4 were just as shocking as those for DF2. By studying the motions of its globular cluster's tight, spherical collections of stars that orbit a galaxy's core, astronomers found them moving at remarkably slow, sluggish speeds. Their velocities were perfectly in line with the gravitational pull generated by the galaxy's visible stars and gas alone. There was no need for any additional, invisible mass to explain what they were seeing. It was as if the universe had, in this one quiet corner, decided to play by a completely different set of rules, building galaxies without the dark matter scaffolding we thought was absolutely essential. This is where the scientific fear truly crystallized. The existence of even one dark matter-free galaxy was a massive problem. The existence of 2 right next to each other was a full-blown crisis. It forced theorists to confront 2 equally terrifying possibilities. The first was that our entire understanding of how galaxies form was fundamentally wrong. Perhaps there was some exotic, unknown mechanism that could gather vast amounts of gas and stars without the gravitational pull of a dark matter halo first drawing them in. The second, even more unsettling possibility was that we were wrong about dark matter itself. Maybe it wasn't a particle that only interacts through gravity, but something else entirely, something that could, under certain conditions, be stripped away or become disconnected from the visible matter it was supposed to be guiding. In the search for an answer, a compelling and elegant solution began to emerge. One that didn't require overturning all of modern physics, but instead revealed a terrifyingly violent cosmic process. This is the tidal stripping hypothesis. Imagine the NGC 1052 group not as a peaceful collection of islands, but as a battlefield where galaxies constantly graze past each other, their immense gravitational fields acting like cosmic sandblasters. In this scenario, both DF2 and DF4 were once normal dwarf galaxies, each with its own healthy halo of dark matter. But they ventured too close to the group's dominant giant, the massive elliptical galaxy NGC 1052. The key to the mystery lies in a fundamental difference between dark matter and normal matter. Dark matter, believed to be collisionless, feels only gravity. It can pass through itself and other matter without friction. Normal matter, the gas and stars, experiences pressure and friction. According to the tidal stripping model, as these doomed dwarfs swung past the giant galaxy, its immense tidal gravity would have begun to tear them apart. But it would have done so selectively, the dark matter halo, being large, diffuse, and attached only by gravity, would have been the first thing to be pulled away, easily stretched and shredded into a vast stream of invisible particles lost to the intergalactic void. The visible matter, the stars, would have been more resilient, held together by their own gravitational bonds and experiencing collective friction. They would have resisted being immediately torn apart, remaining as a cohesive, though now doomed, group. The result is a ghost, a galaxy that looks intact in starlight but has been surgically disemboweled of its dark matter, leaving behind only the visible trappings of a galaxy that is already dead, a corpse whose spirit has already departed. This explanation, while elegant, introduces a new layer of fear. It suggests that the universe is capable of a form of gravitational surgery so precise and so destructive that it can create entire phantom galaxies that fundamentally mislead us. If the tidal stripping hypothesis is correct, then DF2 and DF4 are not proof of a new way to build galaxies. They are celestial mirages, the final fossilized remains of a violent tragedy that occurred billions of years ago. Their existence implies that this brutal process is not rare, and that the cosmic landscape could be littered with such dark matter ghosts, their true nature hidden from us. This forces a humbling realization. When we look at a galaxy, we are only seeing a snapshot in time, a single frame from a billion-year-long movie. We might be completely misinterpreting what we see, mistaking the aftermath of a cosmic disaster for a fundamental truth about the universe's construction. The fear surrounding DF4, therefore, is not just about dark matter, but about our own ability to correctly read the story of the cosmos when the most dramatic chapters have already ended, leaving behind only silent, confusing ruins. While the drama of galactic collisions and tidal destruction unfolds in the NGC 1052 group, our journey now takes us to a far more isolated and serene corner of the cosmos, to a galaxy that embodies the quiet, persistent power of dark matter. Floating in a vast and lonely expanse of intergalactic space, far from the disruptive pull of any major cluster, lies UGC 1378. This low-surface brightness galaxy is the ultimate introvert of the cosmos, a faint, sprawling disk of stars that emits so little light it would be virtually impossible to see with the naked eye even if you were right next to it. Its ethereal glow is so diffuse that it blends almost perfectly with the background sky, a ghostly whisper in the silent void that required the most sensitive telescopes and advanced image processing to even detect. The profound isolation of UGC 1378 is the first key to its mystery. Unlike the galaxies in the chaotic Virgo cluster or those torn apart in galactic groups, this galaxy has existed for billions of years in a state of near-perfect tranquility. It has not been subjected to violent encounters, gravitational harassment, or tidal stripping. It is a cosmic control experiment, a galaxy that has been left entirely to its own devices to evolve according to the fundamental laws of physics, free from external interference. This makes it an incredibly pure laboratory for studying the intrinsic relationship between dark matter and galaxy formation. What we see in UGC 1378 is not a distorted aftermath but a pristine picture of how a galaxy naturally settles when built upon a foundation of dark matter. And what that picture reveals is both astonishing and humbling. Despite its faint appearance, detailed studies of the rotation of its gas and stars show they are moving at incredibly high speeds. This rapid motion means the galaxy must be immensely heavy, with a gravitational grip far stronger than the collective pull of all its visible stars and gas could possibly provide. The only explanation is that UGC 1378 is enveloped in a colossal, massive halo of dark matter, a vast sphere of invisible mass that makes up the overwhelming majority of the galaxy's total weight. This dark matter anchor is what holds the entire faint structure together, preventing its sparse stars from simply drifting apart into the emptiness. It is a classic textbook example of dark matter's dominant role, but seen in a galaxy that has been perfectly preserved like a fossil trapped in amber. The profound challenge in observing a galaxy like this cannot be overstated. Detecting UGC 1378 is like trying to photograph a faint cloud of fireflies from miles away on a foggy night. Astronomers must use long, painstaking exposures with powerful telescopes, often employing specialized filters and processing techniques to subtract the natural glow of Earth's own atmosphere just to tease out the galaxy's faint signal from the background noise. Every piece of data is hard-won, and a single measurement of its rotation curve can require dozens of hours of precious telescope time. This immense difficulty is precisely why scientists fear that galaxies like UGC 1378 are not the rare exception, but could in fact represent the majority of galaxies in the universe. This is the most terrifying implication of all. Our entire map of the cosmos is built upon what we can see. We have catalogued hundreds of billions of galaxies, but every single one of them is, by definition, luminous enough for our telescopes to detect. We have been unconsciously biased, only counting the galaxies that are bright and easy to see, the brilliant cities of the universe. But what if for every bright, star-filled galaxy like our Milky Way, there are 10 or 100 or even 1,000 faint, ghostly counterparts like UGC 1378? What if the universe is absolutely teeming with these dark matter-dominated giants, an invisible majority that forms the true backbone of cosmic structure, while the galaxies we see are merely the rare, well-lit outliers? This fear strikes at the very heart of our attempt to understand the universe's composition and history. If these low-surface brightness galaxies are the true majority, then our census of the universe's mass is catastrophically incomplete. We would have to completely reassess how matter is distributed across space and how galaxies form and evolve. The quiet, isolated existence of UGC 1378 is not just a curiosity. It is a direct challenge to the completeness of our cosmic inventory, a haunting reminder that the universe we see may only be the smallest tip of a vast, dark iceberg. Yet even the sprawling, quiet dominance of UGC 1378 is dwarfed by the sheer scale of our next destination, a dark giant so vast it redefines the very meaning of the word galaxy. This is Malin I, a legendary titan hiding in the constellation Coma Berenices, and it holds the distinction of being one of the largest low-surface brightness galaxies ever discovered. If you were to place it next to our own Milky Way, our galaxy would appear as a compact, brilliant jewel, while Malin I would be a faint, ethereal cloud so enormous its outer edges would stretch far beyond the limits of our entire local group of galaxies. Its sheer physical diameter is staggering, a cosmic leviathan that makes even the largest known spirals seem small by comparison. But its most terrifying feature is not its size, but its profound silence. For a structure of such immense proportions, it emits a pitifully small amount of light, a ghost on a scale that is almost incomprehensible. The paradox of Malin I lies in its baffling composition. This is a galaxy that is incredibly rich in the raw materials for star formation. Observations have revealed that it contains a gargantuan reservoir of neutral hydrogen gas, enough to birth billions upon billions of new stars. In a normal spiral galaxy, such a vast supply of cold gas would trigger an epic firestorm of star birth, lighting up the cosmos with brilliant clusters and nebulae. Yet in Malin I, this gas exists in a state of profound quiescence. It is spread out across an enormous volume, remaining diffuse, calm, and stubbornly unwilling to collapse under its own gravity to form new stars. It's as if the galaxy is a sleeping giant, possessing all the fuel needed to become one of the brightest objects in the universe, but for some reason, the engine of creation simply will not start. This failure to ignite points directly to the invisible hand of dark matter. The prevailing theory suggests that Malin I is embedded within an unthinkably large and incredibly massive halo of dark matter. But unlike the dense, concentrated halos that power star formation in galaxies like our own, Malin I's dark matter halo is thought to be unusually extended and low in density. This creates a gravitational potential well that is incredibly wide but also incredibly shallow. Imagine trying to light a fire not in a compact stone fireplace but spread across an entire open field. The heat dissipates, the fuel never gets concentrated enough to catch, and the entire process fizzles. The gas in Malin I is spread so thin by this vast, weak gravitational field that it simply cannot achieve the critical density needed to begin the process of stellar collapse. The dark matter isn't just present, it is actively suppressing star formation on a cosmic scale through its very structure. This revelation is what truly unsettles astronomers. Malin 1 is not a failed galaxy. It is a galaxy that has been engineered by dark matter to exist in a permanent state of arrested development. Its existence suggests a terrifying diversity in the properties of dark matter halos. We can no longer think of them as simple, featureless spheres of mass. Instead, they appear to have complex architectures, some dense and efficient at forging stars, others vast and diffuse, creating these silent, gas-rich giants. The fear is that Malin 1 might not be alone. It could be the brightest and easiest to see representative of an entire hidden population of ultra-large, low-surface brightness galaxies. These cosmic giants could form a dark, unseen framework throughout the universe, containing a significant fraction of all the cosmic gas that was thought to be missing from our inventories. Malin 1 is a haunting warning that the most massive structures in the cosmos might also be the darkest, and that our understanding of how the universe allocates its resources is still in its earliest, most naive stages. Yet even the immense and silent scale of Malin 1 cannot prepare us for the profound anxiety induced by a tiny, faint smudge of light in one of the most crowded places in the universe. This is Coma P, an ultra-diffuse galaxy nestled within the sprawling, chaotic Coma cluster, and its story is not about confirming our theories, but about tearing them apart with contradictory evidence. Discovered, like Dragonfly 44, by the keen eyes of the Dragonfly telephoto array, Coma P initially appeared to be just another member of this ghostly population, a faint, wispy collection of stars barely holding on in a gravitational maelstrom. But when astronomers turned more powerful telescopes toward it to measure its mass, they were met with a result so baffling it threatened to undermine the very methods we use to explore the cosmos. The standard procedure for weighing a galaxy involves measuring the velocity of its stars or star clusters. Faster motions indicate a stronger gravitational pull, which requires more mass. For almost every other galaxy we've studied, from the mighty Andromeda to the faintest dwarfs, these measurements have consistently revealed a massive dark matter halo, a hidden source of gravity that far outweighs the visible stars. But when researchers used the Keck Observatory to study the motions of 10 glowing clusters within Coma P, they found something utterly unexpected. The clusters were moving slowly, sedately, their speeds perfectly in line with the gravitational pull of the galaxy's meager visible mass alone. The initial calculations suggested that Coma P, against all odds and all established theory, contained little to no dark matter. This single result sent a shockwave of confusion through the scientific community. It wasn't just surprising, it was deeply inconvenient. Here was a galaxy surviving in the most dangerous environment imaginable, the Coma cluster, where tidal forces are so powerful they should instantly shred any object that isn't anchored by a massive dark matter halo. For Coma P to exist without dark matter was like a piece of tissue paper surviving unharmed in the heart of a hurricane. It simply shouldn't be possible. The finding was so bizarre that it immediately raised a red flag. Was Coma P truly an impossible galaxy, or were we, the observers, missing something crucial? This is where the fear truly sets in, a fear not of the galaxy itself, but of our own potential for error. The anxiety surrounding Coma P stems from the terrifying possibility that our most trusted observational techniques might be fundamentally flawed or woefully inadequate when applied to these incredibly faint targets. Measuring the precise velocities of star clusters in a galaxy as dim as Coma P is pushing our technology to its absolute limit. The signal is incredibly weak, a faint whisper of light that must be extracted from a roaring background of atmospheric interference and instrumental noise. The margin for error is enormous. A slight miscalibration, a subtle misinterpretation of the data, or even an unlucky sampling of only the slowest moving clusters could easily produce a result that looks like a lack of dark matter, when in reality, a massive halo is there, hiding just beyond the resolution of our instruments. The subsequent studies only deepened the mystery and the unease. Other teams re-observed Coma P, and their analyses pointed back toward the more traditional conclusion that the galaxy does, in fact, possess a significant dark matter halo after all. The scientific literature now holds these contradictory papers sitting side by side, a direct conflict that remains unresolved. This inconsistency is every astronomer's nightmare. It reveals that when we peer into the darkest corners of the universe, our view is still blurry and our interpretations are still fragile. Coma P is no longer just a galaxy. It has become a symbol of a profound and unsettling humility. It forces us to confront the limits of our own perception, wondering if the universe's deepest secrets are still just beyond our grasp, obscured not by darkness, but by the inherent uncertainty of our own methods. Leaving behind the crowded, chaotic clusters, we now journey into the vast, empty voids between the great galactic filaments, to a place of profound isolation and ancient purity. Here we find KKR-25, a dwarf galaxy so remote and untouched it serves as a living fossil from the dawn of time. Unlike the galaxies entangled in the gravitational dances of clusters and groups, KKR-25 exists in a state of near-total solitude, a lonely island adrift in a sea of darkness. Its isolation is its most defining feature, a guarantee that it has lived a quiet life, undisturbed by the violent collisions and tidal interactions that reshape so many of its cousins. This pristine existence makes it a perfect window into the conditions of the early universe, a cosmic time capsule preserved in perfect amber. The purity of KKR-25 is immediately revealed in the very composition of its stars, or more precisely, what those stars lack. Astronomers measure the metallicity of a star system, the abundance of elements heavier than hydrogen and helium, to understand its history. These heavier elements, which astronomers collectively call metals, are forged in the nuclear furnaces of stars and scattered across the cosmos in violent supernova explosions. A high metallicity indicates a galaxy that has lived a long and productive life, cycling through generations of stars that have enriched it with these heavier elements. KKR-25, however, possesses an incredibly low metallicity. Its stars are made of almost nothing but the pristine hydrogen and helium that were created in the Big Bang. This means the galaxy has undergone very little star formation across its entire existence. It is a primitive, unevolved relic, a snapshot of what the very first galaxies looked like billions of years ago. This primitive state is inextricably linked to its other dominant feature, an overwhelming abundance of dark matter. Measurements of the galaxy's internal dynamics show that its few stars are moving under the influence of a gravitational force far exceeding what their visible mass can account for. KKR-25, like so many other dwarfs, is utterly dominated by its dark matter halo. But here, in this pristine environment, that fact takes on a new and more significant meaning. Scientists believe that in the early universe, dark matter halos were the essential seeds for galaxy formation. The first galaxies were not collections of stars that then attracted dark matter. They were clouds of dark matter whose gravity pulled in the primordial gas, which then condensed to form the first stars. KKR-25 appears to be a frozen example of this very process, a dark matter seed that only managed to form a tiny handful of stars before its development inexplicably stalled. This is where the scientific worry begins. KKR-25 is a direct test of our models of cosmic dawn, the epoch when the first lights in the universe flickered on. Our simulations predict that small, dark matter-dominated halos like this should have been incredibly efficient at forming the first stars. The pristine gas, free of contaminants, was actually supposed to cool more efficiently and collapse more readily into stars. Yet, KKR-25 and other ultra-faint, low-metallicity dwarfs are famously inefficient. They possess the gravitational potential and the raw fuel, but the engine of star formation never truly turned over. This presents a glaring contradiction known as the too big to fail problem on a small scale. The dark matter halos in our simulations are too massive and too potent to have failed so spectacularly at forming stars. The existence of KKR-25 suggests that something is suppressing star formation in these small, primordial halos, a physical process that our current models of the early universe do not adequately capture. The fear is that this fossil galaxy is hiding an uncomfortable truth about the nature of dark matter itself. One leading hypothesis is that dark matter might not be completely cold and inert as we assume. If dark matter particles were slightly warmer, meaning they had a tiny amount of thermal motion, they would resist collapsing into the extremely dense cores predicted by the cold dark matter model. These warmer, fluffier halos would have a shallower gravitational potential well, making it harder to pull in and compress gas to form stars. This would explain the inefficiency we see in galaxies like KKR-25. Another, more dramatic possibility involves the intense radiation from the first generations of stars. The ultraviolet light from these early giants could have heated the primordial gas throughout the entire universe, preventing it from cooling and collapsing into the smaller dark matter halos, effectively sterilizing them and stunting their growth. KKR-25 forces us to confront a humbling possibility. This silent, primitive ghost might be evidence that the foundational seeds of our cosmos, the dark matter halos, are not the simple, predictable structures we've modeled them to be. Their properties could be more complex, and the physical processes that govern the birth of the first stars could be far more nuanced than we ever imagined. By failing to follow the script our simulations have written, this cosmic time capsule implies that the very first chapters of the universe's story may need to be completely rewritten, based on truths we are only beginning to uncover from the darkness. But just as we grapple with the primordial silence of KKR-25, the cosmos presents us with a shape so geometrically audacious it seems to defy the very natural laws that govern it. In the constellation Eridanus, a staggering 70 million light-years from Earth, floats LEDA 074886, a galaxy that has earned the nickname the Emerald Cut Galaxy for its astonishingly rectangular appearance. In a universe dominated by graceful spirals, featureless ellipses, and messy irregular blobs, this galaxy presents itself with sharp 90-degree corners, looking less like a natural celestial structure and more like a cut gemstone or a product of intelligent design dropped carelessly into the void. Its discovery was a moment of pure disbelief for astronomers, a visual paradox that challenged a fundamental assumption that galaxies governed by gravity and rotation should be roughly spherical or disk-like. This geometric oddity is a stark reminder that the universe still holds surprises that can shatter our expectations. The mystery of its shape is deeply intertwined with the invisible hand of dark matter. Current theories suggest that this perfect rectangle is not a static structure but a fleeting moment in a cosmic collision, a delicate and violent dance frozen in time. The prevailing hypothesis is that we are witnessing the aftermath of an incredibly precise, edge-on merger between two smaller spiral disk galaxies. Imagine two thin coins crashing into each other perfectly on their edges, their stars and dark matter interacting in a complex gravitational ballet. During such a collision, the stars, which feel gravitational forces but do not collide with each other, can be flung into wildly elongated orbits, tracing out a box-like shape in the process. The dark matter, which makes up the overwhelming majority of the mass in this system, forms a vast, stabilizing halo that acts like a mold, holding this temporary rectangular structure of stars together long enough for us to witness it. This explanation, while elegant, introduces a profound fear about the stability and predictability of cosmic structures. The rectangular shape of LEDA 074886 is not a permanent feature, it is an ephemeral phase. Gravitational forces will eventually cause this precise distribution of stars to relax into a more common, blob-like elliptical galaxy. The fact that we are seeing it at all is a testament to an incredible cosmic coincidence, a snapshot of a transient event that may only last a few 100 million years, a mere blink in cosmic time. This forces a terrifying question about the limits of our observations. How many other bizarre, temporary galactic structures have formed and dissolved throughout the history of the universe without us ever seeing them? Our entire classification system for galaxies is based on stable, long-lived shapes. LEDA 074886 is a warning that the cosmos might be filled with a zoo of short-lived, exotic forms that our surveys, which capture a single moment in time, are almost certain to miss. The deeper fear, however, lies in the remote possibility that the collision theory is wrong. While it is the most accepted explanation, the precise rectangularity of this galaxy is so extreme that it pushes the limits of what a merger can produce. This leaves a tiny, unsettling door open for more exotic explanations. Could some unknown property of dark matter itself be responsible? What if dark matter, under certain conditions, can exert forces or interactions that we haven't yet dreamed of, forces that could impose such stark geometric order on the visible matter? While this is far less likely than the merger scenario, the mere existence of such a geometric outlier forces scientists to acknowledge the gaps in our understanding. LEDA 074886 stands as a rectangular monument to our ignorance, a perfect shape that reminds us that even the most fundamental rules of galactic architecture might have exceptions written in the dark. Yet the serene beauty of its central starburst is not the true story of NGC 2915. That story begins in the silent, invisible realm beyond the light. When astronomers mapped the rotation of the galaxy's outer hydrogen gas, they expected the velocities to decline with distance from the bright center, following the predictable drop-off of gravitational influence from the visible mass. Instead, they found the opposite. The gas in the outermost regions was racing around at incredibly high speeds, moving so fast that the gravity from all the stars and gas in the entire galaxy combined was utterly insufficient to hold it in place. This rapidly orbiting gas should have been flung out into the void long ago. The fact that it isn't reveals the presence of a hidden anchor, a gravitational force of immense power with no visible source. Calculations show that to account for these motions, NGC 2915 must be embedded within a colossal, sprawling halo of dark matter that is at least 10 times more massive than all of its visible components combined. The brilliant blue core is merely a tiny, glittering bauble sewn onto the edge of an invisible giant. This staggering disconnect between the vibrant inner light and the overwhelming outer darkness is what makes NGC 2915 so profoundly concerning to scientists. It presents us with a galactic schizophrenic, a single object behaving in two completely different ways for reasons we cannot yet fathom. In the core, normal matter is in control, following the rules of physics we understand. Gas collapses, stars ignite, and energy flows. But in the vast, dark outskirts, the rules are being written by the invisible hand of dark matter, dictating the motion of that gas with absolute authority. We are witnessing a cosmic puppet show where the visible galaxy is the puppet and dark matter is the puppeteer, but we have no view of the strings or the hands that pull them. We can see the effects of the manipulation, but the mechanism remains a complete mystery. The fear that NGC 2915 instills is not about its existence, but about what it implies for our models of galaxy evolution. This galaxy is a clear and powerful example of how dark matter governs the overall structure and rotation of a galaxy, yet it offers no clues as to why this governance is so uneven. Why does the dark matter halo allow such ferocious star formation to proceed in the core while enforcing a strict, silent quarantine in the outer regions? Our simulations suggest that dark matter halos should have a smooth, predictable density profile, but the extreme contrast in NGC 2915 hints that the reality might be far more complex. The dark matter could be structured in a way that actively suppresses star formation in the outer disk, perhaps by preventing the gas from cooling and condensing, leaving the core as the only place where the conditions are just right for stellar birth. This suggests a level of influence and interaction between dark and normal matter that our current theories simply do not account for, revealing a terrifying gap in our understanding of the universe's most fundamental architect. But if the vast, quiet expanse of Malin 1 feels like a monument to dark matter's patient power, then our next destination is a true cosmic leviathan, a dark giant so immense it challenges the very limits of what we consider a galaxy. This is UGC 2885, often called the Godzilla Galaxy, a titan of the low-surface brightness world residing in the constellation Perseus. To truly grasp its scale, consider our own Milky Way, a respectable spiral galaxy 100,000 light-years across. UGC 2885 dwarfs it, stretching for an almost incomprehensible 460,000 light-years from end to end. If placed in our neighborhood, its faint outer disk would engulf the entire local group, its ethereal tendrils reaching past the Andromeda Galaxy. Its sheer physical presence is staggering, a behemoth lurking in the cosmic dark. The most immediately unsettling feature of UGC 2885 is not just its size, but its profound tranquility. This is a galaxy that appears to be in a state of deep cosmic slumber. Its spiral arms are incredibly faint and loose, lacking the tight, well-defined structure of younger, more active galaxies like our own. Its disk is remarkably smooth and undisturbed, showing no signs of recent collisions, violent mergers, or the gravitational agitation that typically stirs up star formation. The few stars it has formed are predominantly old, red, and quiet, with very few of the brilliant blue nurseries that signal vigorous new stellar birth. This galaxy exudes an aura of ancient, undisturbed calm, as if it has been slowly turning, almost imperceptibly, for nearly the entire history of the universe, a silent witness to eons of cosmic evolution. This incredibly slow, sedate pace of life is the central clue to its dark nature. For a galaxy of such immense proportions to remain so stable and so quiet, it must be held in an impossibly firm gravitational embrace. The gentle, smooth rotation of its outer hydrogen gas tells the story. That gas is moving at velocities that should easily tear the entire colossal structure apart. The only force powerful enough to prevent this catastrophic disintegration is a truly monumental halo of dark matter, a sphere of invisible mass so vast and heavy that it acts as a cosmic anchor, holding every star and every wisp of gas in its precise, orderly place. The dark matter in UGC 2885 isn't just a component, it is the primary structure. The visible galaxy is nothing more than a faint watermark on the surface of an ocean of darkness. This revelation leads to the most profound and unsettling fear that this galaxy represents. UGC 2885 is not a bizarre outlier. Many astronomers now suspect it may be the ultimate prototype. It could be the leading example of a vast, hidden class of galaxies that form the true backbone of the cosmic web. Our current census of the universe is overwhelmingly biased toward galaxies that are bright, active, and easy to see. We have built our understanding of cosmic evolution on the study of these brilliant objects. But what if they are the exception? What if the universe is actually dominated by these gigantic, dark matter-rich, low-surface brightness galaxies? These silent, slow-moving titans that contain the majority of the universe's normal matter in the form of thinly spread gas. The terrifying implication is that we may have been misreading the universe's story entirely. We see the brilliant, flashy bursts of star formation in smaller galaxies and assume that is where the primary action is. But UGC 2885 suggests the real story is one of quiet, dark dominance. These galaxies, by virtue of their immense dark matter halos and stable environments, could be the universe's primary reservoirs of neutral hydrogen gas, the raw fuel for future star formation. They represent a potential future for galaxies, a state of quiet equilibrium that most will eventually settle into as the frenetic energy of their youth fades away. The fear is that our maps of the cosmos are catastrophically incomplete, missing the largest and most massive structures simply because they don't shine brightly enough for our telescopes to easily see. UGC 2885 is not just a galaxy, it is a warning that the true rulers of the cosmic web may be hiding in plain sight, their immense power revealed not by light, but by the silent, unwavering grip they hold on the fabric of space itself. Yet the sheer size and quiet power of UGC 2885 cannot fully prepare us for the stark and lonely beauty of our next destination, a galaxy that redefines the concept of isolation. Drifting in the immense, empty void between the great superclusters, far from the gravitational pull of any major galaxy group, lies DGS T1. This ultra-diffuse galaxy is the ultimate cosmic hermit, a solitary smudge of light in an ocean of blackness so vast that its nearest neighbors are millions of light years away. It was discovered not by its starlight, which is incredibly faint, but by its faint emission of specific wavelengths of light that revealed its unique nature. Its extreme isolation is its most defining and puzzling feature, a condition that makes its very existence a profound challenge to our understanding. The mystery of DGS T1 deepens when we examine its structure. Unlike many faint galaxies that are mere blobs of old stars, this one possesses a large, bright, and surprisingly compact core relative to its incredibly faint and extended outer halo. This gives it an almost ghostly eye-like appearance, a brilliant pupil surrounded by a vast, ethereal iris. But the most startling discovery came when astronomers trained the powerful lenses of the Hubble Space Telescope upon it. They found that DGS T1 is accompanied by an unusually large population of globular clusters for a galaxy of its diminutive brightness. Globular clusters are dense, spherical collections of hundreds of thousands of ancient stars that typically orbit the cores of large galaxies like the Milky Way. For a faint, ultra-diffuse galaxy to host such a rich system of them is completely unexpected. It's like finding a small, remote village that somehow possesses the crown jewels of a vast empire. This bizarre combination of properties, isolation, a compact core, and a rich globular cluster system is what fuels intense scientific debate and concern. There are two leading and equally unsettling theories for its origin. The first is that DGS T1 is a failed giant, a fossil from the dawn of time. In this scenario, it began its life as a much more massive galaxy, a proto-galaxy that formed very early in the universe's history. But for reasons unknown, it failed to attract and retain enough gas to fuel significant star formation across its vast expanse. Its bright core is the sole remnant of that initial, aborted burst of activity, and its globular clusters are the surviving relics of that early, more productive era, left behind like monuments to a greatness that never was. The second, more violent theory is that DGS T1 is the ghost of a catastrophic collision. Imagine two galaxies, perhaps smaller precursors to a larger spiral, engaging in a gravitational dance that ends in a direct head-on merger. The violent interaction could have violently stripped away their gas and shredded their outer stars, scattering them into a vast, diffuse halo. The surviving cores of the two galaxies would then have merged to form the single, bright central region we see today, while the gravitational turmoil of the event flung the globular clusters into wide, distant orbits. This would make DGS T1 not a failed galaxy, but a galactic wreck, a celestial automobile accident frozen in time, with its globular clusters acting as the scattered debris from the impact. The fear that DGS T1 instills in scientists stems from this very ambiguity. Its isolated location makes it incredibly difficult to study, and its strange properties refuse to neatly fit into either category. If it is a failed giant, it suggests that the early universe was capable of forming massive dark matter halos that for some reason never ignited, meaning our models of the conditions in the primordial cosmos are missing a critical piece of physics. If it is a merger remnant, its isolation is a massive puzzle, as such violent encounters are expected to occur within dense galaxy groups, not in the lonely voids of intergalactic space. This would imply that our understanding of galactic evolution and the environments where mergers can occur is far too limited. DGSA-T1 forces a humbling realization. This solitary, enigmatic object proves that the universe can forge galaxies through processes we have not yet witnessed or predicted. Its existence in the void suggests that the cosmic backwaters, far from the bright cities of galaxy clusters, might hold the keys to understanding the most extreme and rare forms of galactic evolution. It is a single, faint question mark hanging in the dark, challenging us to explain how such a contradictory and lonely object could ever come to be. Yet the profound isolation of DGSA-T1 offers a stark contrast to our next destination, a galaxy that presents a different kind of mystery, one not of loneliness but of hidden abundance. Tucked away in the constellation Ursa Major lies NGC 3741, a humble dwarf irregular galaxy that serves as a powerful reminder that true cosmic wealth isn't always measured in starlight. At first glance, this small, messy collection of stars seems utterly unremarkable, a faint smudge easily overlooked in surveys dominated by grand spirals and brilliant ellipticals. But when astronomers began to weigh its components, they discovered that NGC 3741 is a galactic miser, hoarding a secret treasure of unimaginable proportions. This unassuming dwarf is staggeringly rich in neutral hydrogen gas, the primary fuel for star formation, possessing a reservoir so enormous it completely defies all expectations for an object of its size and luminosity. The numbers involved are so extreme they border on the unbelievable. In a typical galaxy like our Milky Way, the mass of stars outweighs the mass of interstellar gas by a factor of about 10 to 1. In NGC 3741, this ratio is completely inverted. The mass of its hydrogen gas is a full 15 times greater than the combined mass of all its stars. This gives it one of the highest gas-to-stellar mass ratios ever observed in the known universe. Imagine a small town whose entire economy and infrastructure is built around a single, quiet factory, while beneath the town lies a vast, untapped oil field containing 100 times more potential energy than the town itself currently uses. That is the paradox of NGC 3741. It is sitting on an epic stockpile of fuel, yet it shows only a trickle of ongoing star formation, a quiet, inefficient sputtering that does nothing to deplete its immense reserves. This hoard of gas is the key that unlocks the galaxy's true nature and reveals the invisible force that dominates it. To understand why this gas hasn't collapsed to form new stars or simply drifted away into intergalactic space, astronomers measured the rotation of this vast reservoir. They found the gas whipping around at tremendous speeds, velocities that should instantly fling it out into the void. The only possible explanation is that the entire galaxy is ensnared within an immensely powerful and massive dark matter halo, a gravitational anchor of such strength that it can hold onto this colossal cloud of fuel against all physical odds. The dark matter in NGC 3741 isn't just present. It is the primary reason the gas is there at all, acting as a cosmic storage container that has preserved this primordial material for billions of years. This immense, hidden mass is what makes NGC 3741 a critical test case for our models of dark matter. The galaxy's rotation curve, a graph plotting the orbital speed of its gas against the distance from the center beautifully and precisely matches the predictions of the cold dark matter model on a small scale. It shows a rapid rise in velocity followed by a flat, sustained high speed far out into the halo, a classic signature of a dominating, unseen mass. In this way, NGC 3741 is a triumph for cosmology, a textbook example that confirms our basic understanding of how dark matter governs galactic dynamics. It provides a clear, clean laboratory for studying the relationship between a dark matter halo and the gas it so effectively retains. However, this very success introduces a deeper and more worrying puzzle known as the missing baryons problem. Baryonic matter is the term for ordinary matter, the protons, neutrons, and electrons that make up stars, gas, planets, and us. While we know dark matter makes up about 85% of the universe's mass, we also know that a significant fraction of the remaining 15% of ordinary matter is unaccounted for. Our inventories of stars and hot gas in galaxies and clusters simply don't add up to the total amount of baryons that should exist based on our measurements of the early universe. Galaxies like NGC 3741 might be hiding a large portion of the answer. Its immense gas reservoir is almost entirely composed of cold, neutral hydrogen, a form of baryonic matter that is notoriously difficult to observe at great distances. This leads to the most profound concern this galaxy represents. If the cosmos is filled with countless dim, gas-rich dwarfs like NGC 3741, each harboring a huge hidden stockpile of ordinary matter in the form of cold gas, then our census of the universe's baryonic content is critically incomplete. We have been searching for the missing ordinary matter in the wrong places, looking for hot gas in galaxy clusters or ionized plasma between galaxies, when a substantial portion of it might be right here, locked away in the dark, silent halos of these unassuming dwarfs. They are the cosmic equivalent of secret bank vaults, holding a fortune in plain sight that we lack the tools to recognize. NGC 3741 forces a humbling realization that even the familiar ordinary matter in the universe possesses a talent for hiding, suggesting that the true distribution of the cosmos's building blocks may be far more complex and concealed than we ever imagined. Yet even the profound mysteries of Andromeda 25 cannot fully prepare us for the enigmatic nature of its celestial neighbor, a ghost so faint it pushes the very limits of detection. This is Andromeda 5, a dwarf spheroidal galaxy clinging to the gravitational apron strings of the mighty Andromeda Galaxy, and it embodies the quiet, stubborn challenges that dark galaxies present to modern science. Discovered in the data of the Sloan Digital Sky Survey, Andromeda 5 registered as little more than a subtle statistical fluctuation, an almost imperceptible clustering of a few thousand ancient stars against the overwhelming blackness of space. Its appearance is the very definition of unassuming, a cosmic afterthought that holds secrets far greater than its faint light would ever suggest. The first clue to its profound darkness lies in the very composition of its stars. Astronomers measure a property known as metallicity, the abundance of elements heavier than hydrogen and helium. To understand a galaxy's history, these heavier elements are forged in the hearts of stars and scattered by supernova explosions, so a low metallicity indicates a system that has undergone very little star formation across its entire existence. The stars in Andromeda 5 are among the most metal-poor ever observed. They are primitive, ancient relics made almost entirely of the pristine hydrogen and helium created in the Big Bang. This reveals a galaxy that has been in a state of arrested development for billions of years, a place where the cosmic engine of creation never truly kicked into gear, leaving behind a silent, unevolved fossil from the dawn of time. This primitive state is inextricably linked to the galaxy's most dominant feature, an overwhelming abundance of dark matter. To understand this, astronomers must perform a delicate and incredibly difficult task, measuring the motions of Andromeda 5's sparse stars. Each star is a distant, faint pinprick of light, and determining its velocity requires splitting its light into a spectrum, and looking for tiny shifts in wavelength caused by its motion toward or away from us. For a galaxy this dim, this process pushes our most powerful telescopes to their absolute limits. It requires dozens of hours of observation time on instruments like the Keck or Gemini observatories just to gather enough light from a handful of stars to get a statistically meaningful result. The margin for error is enormous, and the data is often plagued by noise and uncertainty. Yet, the results of this painstaking work are consistently shocking. The few stars that can be measured are moving at velocities that are far too high for the gravitational pull of their visible mass to contain. The calculations point to a single, inescapable conclusion. Andromeda 5, like so many of its faint cousins, is utterly dominated by a massive, dense halo of dark matter. The visible stars are mere tracers, a handful of flickering candles caught in the immense, invisible web of the universe's most mysterious substance. This galaxy is not a collection of stars with some dark matter. It is a dark matter halo that has, almost as an afterthought, collected a few stars. This is where the scientific fear truly takes root. Andromeda 5 is not a unique anomaly. It is a perfect example of the predicted population of ultra-faint, dark matter-dominated dwarf galaxies that should swarm around large hosts like Andromeda and our own Milky Way. These galaxies are critical to our understanding of dark matter because their simplicity makes them ideal natural laboratories. Unlike large spirals with complex histories of mergers and bursts of star formation, these faint dwarfs are relatively pristine. Their dynamics are governed primarily by the gravitational pull of their dark matter halos, offering a cleaner signal to study the properties of dark matter itself. They are the key to testing the cold dark matter model on small scales, potentially revealing whether dark matter is truly cold and non-interacting, or if it possesses more complex, unknown properties. The terror, however, lies in the sheer difficulty of studying them. Andromeda 5 represents a frontier where our observational capabilities are stretched to their breaking point. Its extreme faintness means that any measurement of its mass and structure is fraught with uncertainty. We are trying to decipher the laws of the universe by studying ghosts, and our tools are frustratingly blunt for such a Chinese letter task. This leads to a deeply concerning possibility that the very objects that hold the answers to the dark matter puzzle might be forever beyond our reach, their secrets locked away by their own profound darkness. We fear that our understanding of the cosmos's fundamental nature is being limited not by our theories, but by the cruel irony that the most important clues are also the most difficult to see. Yet the silent, ancient stars of Andromeda 5 offer a stark contrast to our next destination, a galaxy that presents a paradox of ongoing yet bafflingly inefficient creation. Drifting in the constellation Pegasus, a mere 3 million light-years from Earth, is the Pegasus Dwarf Irregular Galaxy, or Pegasus DIG. This small, messy cloud of stars is the epitome of cosmic disorganization, lacking the graceful spiral arms or defined elliptical shape of its more structured cousins. It appears as a chaotic splash of light against the dark canvas of space, a place where star formation sputters along in a seemingly haphazard and unproductive fashion. But this unassuming irregular dwarf holds a secret that belies its messy appearance. It is gripped by an immense and powerful dark matter halo, a hidden force that is both the source of its existence and the reason for its puzzling inefficiency. The story of Pegasus DIG is written in the ages of its stars, a historical record that reveals a tale of fits and starts. Unlike the primitive fossils of other dark dwarfs, Pegasus DIG shows evidence of multiple, distinct epochs of star formation. There is a population of very old stars, ancient relics that formed billions of years ago. But there are also pockets of much younger, brighter blue stars, indicating that stellar birth has occurred in sporadic bursts throughout the galaxy's long history, with the most recent episode happening just a few 100 million years ago, a mere moment in cosmic time. This proves that the galaxy has never fully run out of fuel. It has always retained enough gas to occasionally spark new life. Yet, these bursts are always short-lived and never become a self-sustaining firestorm. The galaxy seems stuck in a cycle of unfulfilled potential, forever on the verge of a breakthrough that never quite arrives. This frustrating inefficiency is directly tied to the invisible architecture of its dark matter halo. Measurements of the galaxy's rotation show that its gas and stars are moving under the influence of a gravitational force far exceeding what their visible mass can account for. Pegasus DIG is utterly dominated by dark matter. However, the structure of this halo appears to be critical. Unlike the dense, compact halos that efficiently funnel gas into star-forming regions, the halo around Pegasus DIG is thought to be more extended and less concentrated. This creates a shallower gravitational well, a wider, more gentle bowl that fails to compress the galactic gas to the critical densities needed for vigorous, continuous star formation. The gas is there, but it remains too spread out and too calm to collapse en masse. The dark matter provides the anchor that holds the galaxy together, but it also provides a structure that actively suppresses its growth, creating a state of permanent, quiet underachievement. This revelation leads to the most profound concern that Pegasus DIG represents for astronomers. Its very existence suggests that this type of galaxy, the irregular, dark matter-dominated and sporadically star-forming dwarf, might not be a rare oddity at all. In fact, it could be the most common type of galaxy in the entire universe. Our current maps of the cosmos are overwhelmingly biased toward bright, active, and easy-to-see objects. We have built our understanding of galactic evolution by studying the brilliant spirals and ellipticals that dominate our catalogs. But what if these are the cosmic equivalent of loud, flashy celebrities, while the true majority of galaxies are the quiet, dim introverts like Pegasus DIG, simply going about their business in the background unnoticed? The fear is that our cosmic census is catastrophically skewed. If the universe is teeming with countless faint, irregular dwarfs, each harboring a significant mass of dark matter and a large reservoir of unused gas, then our entire accounting of the universe's mass and structure is wrong. We would have to completely reassess how ordinary matter is distributed and how galaxies evolve over time. The Pegasus Dwarf Irregular Galaxy, a seemingly unremarkable smudge of light in our local neighborhood, forces us to confront a humbling possibility that the grand, bright galaxies we study may be the exceptions, and the true cosmic story is one written in faint light and dark matter, a narrative we are only just beginning to decipher. But just as we begin to categorize galaxies into neat boxes of ancient fossils or chaotic irregulars, the universe presents us with a hybrid that defies simple classification, a cosmic chimera that forces us to rethink the entire life cycle of these island universes. This is Leo T, a dwarf galaxy a mere 1,300,000 light-years away in the constellation Leo, and it holds the remarkable distinction of being both one of the smallest and one of the most fascinating galaxies in our local group. Leo T is a living paradox, a celestial object that simultaneously exhibits features of a vibrant youth and a dignified old age, blending them in a way that challenges our most fundamental ideas about how galaxies are supposed to evolve over billions of years. The first clue to its dual nature is written in its stars. When astronomers peer into the heart of Leo T, they find two distinct stellar populations living side by side. The first is a group of extremely ancient stars, over 10 billion years old, which are incredibly metal-poor. These relics hail from the earliest epoch of star formation, a time when the universe was still young and pristine. Their presence marks Leo T as a primordial fossil, a galaxy that has been around since nearly the beginning. But alongside these ancient citizens is a second, much younger population, bright, blue, massive stars that are less than 1 billion years old, and a significant reservoir of neutral hydrogen gas that is actively collapsing to form new stars even today. This combination is incredibly rare. Most ultra-faint dwarfs like Segue 1 exhausted their gas eons ago and now consist solely of ancient stars. Leo T, by contrast, has somehow retained its gas and maintained a trickle of star formation across nearly the entire history of the universe, making it a miniature laboratory of continuous cosmic evolution. This delicate, ongoing dance of creation is entirely dependent on the invisible hand of dark matter. For a galaxy this small and faint, to hold onto its gas for so long is a monumental challenge. Intergalactic winds, radiation from other galaxies, and internal supernova explosions should have easily stripped away its gaseous fuel supply billions of years ago. The fact that it hasn't happened points to a formidable, unseen guardian. Detailed studies of Leo T's dynamics reveal that it is embedded within a substantial dark matter halo. This halo provides the gravitational muscle to retain its gas reservoir against all external and internal threats, acting as a protective cocoon that has allowed this tiny galaxy to nurture its stellar nursery for eons. The dark matter isn't just a component, it is the reason Leo T has been able to lead such a long and productive life. This unique balance of gas, stars, and dark matter is what makes Leo T so profoundly important and for scientists so deeply challenging. It exists in a sweet spot of galactic evolution, a place where it has just enough dark matter to protect its gas, but not so much that it triggers rapid, explosive star formation that would quickly exhaust its fuel. It is a galactic slow burner, a thrifty user of its resources that has achieved a sustainable equilibrium. This presents a direct problem for our simplistic classification models, which often place galaxies into binary categories: star-forming or quiescent, gas-rich or gas-poor, primordial or evolved. Leo T is all of these things at once. It forces us to acknowledge that galactic evolution is not a linear path but a complex tree with many branches, and that a galaxy's destiny is shaped by a delicate interplay between its mass, its environment, and its history. The fear that Leo T inspires is not one of menace but of complexity. Its existence suggests that there is a whole spectrum of galactic lifestyles between the bright giants and the dark fossils, and that we have only just begun to map this diversity. If objects like Leo T are more common than we thought, then our understanding of how galaxies live and die is far too simplistic. It hints that the universe might be filled with such hybrid systems, each following its own unique evolutionary path dictated by the subtle and still mysterious properties of its dark matter halo. Leo T is a quiet, unassuming galaxy that carries a monumental message. The cosmos refuses to be pigeonholed, and the true story of galaxy formation is far richer, more nuanced, and more beautiful than our tidy models have yet been able to capture. As we continue our journey into the faintest structures of the local universe, we encounter an object that embodies the very limits of classification. A cosmic Rorschach test that challenges the definitions we so heavily rely upon. This is Willman 1, an ultra-faint system discovered in 2005 within the data of the Sloan Digital Sky Survey, and it sits in a profoundly ambiguous state between two entirely different cosmic identities. Is it a dwarf galaxy, a gravitationally bound island of stars held together by a massive halo of dark matter? Or is it merely a star cluster, a collection of stars born from the same cloud and orbiting each other without the need for any invisible glue? This seemingly academic question is far more than simple semantics. Its answer strikes at the heart of how we understand the role of dark matter in structuring the universe on the smallest scales. The core of the mystery lies in Willman 1's contradictory properties. In terms of its physical size and the number of stars it contains, it looks suspiciously like a globular cluster. These are typically tight, spherical swarms of up to 1 million ancient stars that orbit the cores of larger galaxies like our Milky Way. They are believed to be almost devoid of dark matter, their stars held together solely by their mutual gravitational attraction. Willman 1, however, is far more extended and diffuse than a typical globular cluster. Its stars are spread out over a larger volume of space, and their motions, as best as we can measure them, hint at something peculiar. The velocities of its stars appear to be slightly too high to be explained by the gravitational pull of the visible stars alone. This is the classic signature that has revealed dark matter in countless dwarf galaxies, suggesting that Willman 1 might need a hidden mass component to keep it from flying apart. This ambiguity is precisely what makes Willman 1 such a frightening object for astronomers. It exists in a troubling gray area, a cosmological purgatory where our standard tools for classification begin to break down. If we cannot definitively say whether an object is a dark matter-dominated galaxy or a simple star cluster, then our entire framework for understanding the population of small celestial structures becomes unstable. The fear is not about Willman 1 itself, but about what it represents. A potential entire population of borderline cases that we have been blindly categorizing one way or the other based on incomplete data. How many other objects in our catalogs have we mislabeled? Have we been calling some star clusters dwarf galaxies and inflating the count of dark matter structures, or vice versa? This confusion directly impacts one of the most significant challenges in modern cosmology, the missing satellites problem. Our sophisticated simulations of the universe based on the cold dark matter model predict that a galaxy the size of the Milky Way should be surrounded by many hundreds, if not thousands, of small dark matter halos. Yet, we have only found a few dozen definite dwarf galaxy satellites. One proposed solution is that the majority of these halos are simply too inefficient at forming stars, leaving them almost completely dark and invisible. However, another possibility is that we are seeing some of them but misinterpreting their nature. Objects like Willman 1 could be the key. If it is a star cluster, then it doesn't help solve the problem. But if it is a dwarf galaxy, then it would be one of the faintest, most dark matter-dominated ones ever found. A direct example of the predicted population of failed dark halos that are so inefficient they only manage to form a handful of stars. The profound difficulty in resolving this debate highlights a terrifying limitation in our observational capabilities. Willman 1 is so faint and contains so few stars that measuring the precise velocities of its individual members is a Herculean task. Each measurement has a large margin of error, and we simply do not have enough data points to draw a statistically rock-solid conclusion about its total mass. We are trying to solve a fundamental cosmic mystery by studying a handful of faint pinpricks of light at the very edge of detection. This forces a humbling admission that some of the universe's most important secrets may be locked within objects that are forever on the threshold of what our technology can decipher. Willman 1 stands as a silent, fuzzy sentinel at the frontier of our knowledge, a reminder that the cosmos is under no obligation to make itself easily understandable to us, and that the line between a galaxy and a star cluster can be vanishingly thin, drawn in the faintest ink of starlight and shadow. If the haunting ambiguity of Willman 1 leaves us questioning our most basic classifications, then our final destination on this journey into the dark removes all doubt, presenting us with a cosmic object so faint it defines the absolute extreme of what we can even call a galaxy. This is Segue II, a name that literally means to follow, as it was discovered in the wake of the Sloan Digital Sky Survey's vast data collection. To call it dim would be a catastrophic understatement. Segue II is one of the least luminous galaxies ever identified, a wispy collection of barely 1,000 ancient stars adrift in the vast gravitational field of our own Milky Way. Its total light output is less than that of a single bright star within our own galaxy. If you were to stand within it, the concept of night would lose all meaning. The sky would be an almost perfect black, punctuated by a few dozen faint, distant pinpricks, with the majestic arc of the Milky Way itself dominating the view, a terrifying reminder of your tiny, isolated place in a much larger system. The sheer physical smallness of Segue II is its first bewildering feature. This is not a sprawling giant like Malin I or a diffuse cloud like Crater II. It is a tiny, compact nugget of stellar existence, spanning a mere 30 light-years across. To put that in perspective, you could fly from one end of Segue II to the other in less time than it takes a beam of light to travel from our Sun to the distant Voyager 1 probe. It is a galaxy in the most minimalist sense possible, a handful of stars clinging to each other in the immense void. This minuscule size makes its very survival a profound mystery. A structure this small and lightweight should be incredibly fragile, easily dissolved by the immense tidal forces of the Milky Way's gravity. The fact that it hasn't been instantly shredded and scattered suggests it possesses a hidden source of incredible strength. That strength, of course, comes from an overwhelming dominance of dark matter. When astronomers measured the motions of Segue II's sparse stars, they found them whipping around at velocities far too high for their collective visible gravity to contain. The calculations that followed revealed a mass-to-light ratio that is nothing short of staggering. For every single photon of light its stars emit, there is an incomprehensible amount of invisible mass holding the entire system in a vice-like grip. Segue II is not just a galaxy with some dark matter. It is a concentrated knot of pure dark matter that just happens to have a few stars tragically caught in its gravitational web. It represents the ultimate end of the galaxy spectrum, a place where the visible universe is reduced to a barely perceptible footnote on a page written almost entirely in darkness. This extreme nature is what makes Segue II so deeply significant and, for scientists, so deeply frightening. It is not an anomaly, it is a prototype. Its existence provides the most compelling evidence yet for a critical prediction of the cold dark matter model, that the universe should be teeming with countless ultra-faint, dark matter-dominated halos. These structures are the fundamental building blocks of the cosmic web, the very seeds from which larger galaxies like our own were assembled. Segue II is a pristine example of one of these primordial seeds, a fossil from the dawn of structure formation that has somehow survived to the present day, largely unchanged. It is a direct solution to the infamous missing satellites problem, proving that the predicted swarms of dark halos aren't missing at all. They are everywhere, but they are so inefficient at forming stars that they are almost completely invisible to our telescopes. The fear this instills is not about Segue II itself, but about the scale of our own ignorance. If this one tiny object represents an entire class of cosmic structure, then the universe must be filled with countless such dark entities. For every brilliant spiral galaxy like Andromeda, there could be 100 or 1,000 or even 1,000,000 Segue IIs drifting silently in the darkness, each a massive halo of dark matter with only a handful of stars or perhaps none at all. This means our entire census of the universe, a map built upon the light we can see, is catastrophically incomplete. We have been studying the illuminated tips of a vast, dark iceberg, completely unaware of the immense hidden structure that lies beneath. Segue II is the faintest of whispers, forcing us to listen to a terrifying truth. The cosmos we see is only the smallest fraction of the cosmos that is actually there, and the true rulers of the gravitational realm are silent, dark, and beyond our current ability to fully perceive. And so our journey through the shadows comes to a close, but the profound unease these 25 dark galaxies instill in the scientific community only deepens. We have ventured from the ghostly Leviathan Dragonfly 44 to the impossibly faint whisper of Segue II, and at every turn these cosmic phantoms have defied our expectations. Their very existence is a relentless challenge, a chorus of silent questions echoing from the void. They are not merely curiosities, they are direct evidence that our most fundamental theories about the universe's architecture are at best incomplete. The fear they inspire is not one of celestial monsters lurking in the dark, but a far more profound anxiety about the limits of our own comprehension. We built the lambda-cold dark matter model to explain the cosmos, and it works brilliantly on the grandest scales, predicting the vast cosmic web of filaments and clusters with stunning accuracy. Yet in the quiet, dim realms of these dark galaxies, the model consistently falters, presenting us with puzzles like the core cusp problem and the shocking existence of objects that appear to lack dark matter entirely. This disconnect forces a humbling realization. We are like cartographers trying to map a continent by only studying its brightest, most accessible cities, while ignoring the vast, dark hinterlands that make up most of its territory. These dark galaxies are that uncharted wilderness. They suggest that dark matter itself may be far more complex than the simple, inert scaffolding we've imagined. Perhaps its particles can interact through unknown forces, or maybe the violent history of galactic evolution has sculpted dark matter halos into shapes our simulations cannot predict. The eerie properties of these systems, their impossible diffuseness, their unexpected lack of star formation despite abundant fuel, their sheer ability to hide in plain sight, all point to a universe that is actively concealing its true nature from us. Our exploration has revealed that the cosmos we see is merely the smallest tip of a vast, dark iceberg. For every brilliant spiral like our Milky Way, there could be thousands of these faint, massive ghosts, silently dictating the gravitational dance of the cosmos from the shadows. They are the unseen majority, the true backbone of the cosmic web, and until we can account for them, our understanding of the universe's mass, its history, and its ultimate fate will remain fundamentally flawed. These 25 dark galaxies are not the end of the mystery, they are the beginning. They are the signposts pointing toward a deeper, darker reality, compelling us to build better telescopes, devise more sensitive detectors, and ultimately to rethink everything we